everybody. Today I'm going to talk to you guys about free fall. Now, free fall is not just a ride at an amusement park. It's actually a condition in which objects find themselves when we kind of eliminate air resistance and we allow objects just to fall. So they're able to fall freely, which is where the name comes from, without the influence or the changes that occur when the object is experiencing air resistance. So is this a very realistic situation? Probably not, but that's okay. It makes the math a little bit easier, and we can use it as an approximation for how things will actually fall if the object is not very large, doesn't have a large volume for a small weight. In other words, has a decent amount of density, you might say. So it's important to remember, though, whenever you have a situation like this, that Newton's second law applies. That let's say you have this situation where you have a box that's sitting on a surface, and so therefore the box is being pulled down by the Earth's gravitation, of course. That's its weight. And then it's being supported by the surface itself, which we call a normal force. And we know that under normal conditions, if the surface is horizontal, those two should cancel each other out. So we're not worried about either of those. But let's say that there is an applied force that's moving to the right. That applied force is not canceled out by anything, and therefore it's a net force. That net force causes an acceleration due in the respect of Newton's second law. So if we wanted to use Newton's second law to be able to calculate it, we could. The net force is equal to the mass of the object times its acceleration. So quite easily, to solve for the acceleration, all we would need to do would be to divide both sides by the mass. And so we have an acceleration equals the net force divided by the mass. The net force is the cause of the acceleration, the mass is a resistance to the acceleration, and what's left over is the acceleration itself. So this is a situation we find ourselves in the first condition. In the second condition, we say we have just an object with only one force acting on it, and that one force is the gravitational force. In other words, this is what you would feel if you could pull all the air out of a room and then allow an object to fall. So there would be no other forces acting on it. Now, that's not technically true, but it's close enough to being true that we can kind of make that approximation. So if there's only one force acting on it, that force is not canceled by anything, and so therefore that force is the net force. And so we can plug that net force, in this case the gravitational force, in Newton's second law, and we end up with the gravitational force is equal to the mass times the acceleration due to gravity. Now, we've been dealing with this acceleration due to gravity a number of times. That's our little g value, which is 9.81 meters per second down. What that means is that any object that falls with any mass, doesn't matter what the mass is, doesn't matter what the weight is, any object will experience an increase in its velocity as it falls of 9.81 meters per second for every second that it falls. So, giving an example of this. Let's say we have an object, and it starts from rest here at the beginning. So v1 equals 0, and we allow it to fall. And so after 1 second, so this is 1 second, it falls a certain distance. We don't know the distance yet, but we could calculate it if we wanted to. And now its new velocity has increased in the downward direction by 9.81 meters per second. After 2 seconds, so now it's, let's say, down here, so now we have a 2-second division, like so. Now the new velocity is 9.81 plus 9.81, or 19.62 meters per second. Oops, sorry, meters per second. There we go. There it is. So what happens is every second that the object falls, it increases its speed by this 9.81 meters per second. That's what an acceleration is, and specifically that's what the acceleration due to gravity means. Now there is a different way to think about the acceleration due to gravity. This is an important one, and it's one that we're going to use a lot in this class, so get used to that. That's what's happening here. But there's a different way to think about it. We'll talk about it in just a minute. I do want to head one thing off at the pass if I can, and that is, does this equate to the fact that it fell 9.81 meters in that 1 second? And the answer to that is no. That is not true. So let me show you. It travels for 1 second. It starts at 0 and it ends at 9.81 meters per second. So on average, during this time, it was traveling at 4.905 meters per second for 1 second. And so if you travel at a velocity of 4.905 meters per second, and you do so for 1 second, you may remember that the displacement of an object is equal to its velocity times how long it's going at that velocity. So we can easily go ahead and calculate that out. 4.905 meters per second times 1 second gives us the idea that it has fallen a distance of 4.905 meters. So I'm going to go ahead and write this right here. So this is at 4.905 meters down. That's how far it has fallen. Every object, if it has fallen for 1 second under free fall conditions, which means no air resistance, will fall 4.905 meters in the first second. How far does it fall in the second second? Do I just multiply that by 2? No. I have to use the same average velocity technique to try to figure this out. And so it starts at 0, and it goes all the way down here to 19.62. On average, it was traveling 9.81 meters per second. It was doing that for 2 seconds, though. So 9.81 meters per second for 2 seconds, we plug that in. 9.81 times 2 gives us a position right here of 19.62 meters. Now this might be confusing because you might notice that it's also going 19.62 meters per second right at that last instant. So it's just a coincidence that works out for only this one time that the distance it's fallen and the speed it's going at that particular moment after 2 seconds are the same. That's only a coincidence. It doesn't happen very often that way. So, it only happens this one time that way, so be careful. I could prove it to you by having one more point here. So all the way down we have a 4th time. So this would be right there. So this would be after 3 seconds. The object is all the way down there. So our 4th velocity that we measure after 3 seconds is going to be 9.81 meters per second plus 9.81 meters per second plus 9.81 meters per second, or a total of about 28 meters per second. So I'm not going to worry too much about the sig figs here. So it's about 28 meters per second. And so the question then is, how far did it travel at that time? So if I go all the way from here, 0, down to here, on average it was traveling about 14 meters per second. Oops. Zero plus 28 divided by 2 is 14. So it was on average about 14 meters per second for 3 seconds. And so how long does that, how far does it go in 3 seconds? Well, 3 times 14 is 42 meters. So it's fallen approximately 42 meters on the 3rd second. This one you'd have to do out for more sig figs, but I was kind of approximating there. So that's what we've got. You can see this velocity, this velocity here at the end of the 3 seconds, and the distance it's fallen, 42 meters, very different numbers. So the only time that it actually coincides right here is the particular instance at the 2 second mark. But that's how we do it. So hopefully this makes sense. If you have any questions, please go ahead and let me know. Okay. So the last aspect of the acceleration due to gravity is to think about it like it's a conversion factor. And so what you can think about is this. If we go back to Newton's second law, F equals ma, we use it for gravitation in particular. We get the weight, F, the gravitational force, same thing, equals the mass times the acceleration due to gravity. In chemistry, you might have used mass and weight interchangeably. The reality of that is that they are not the same number. And in physics, there's very big differences between a mass, which is how much matter something has, and a weight, which is how much the Earth is pulling. And so sometimes we have to convert between the two. And so we can use Newton's second law, F equals m times a. But the a that we're using right here is 9.81 meters per second. So we can substitute in the little g for that. So you can think about little g as a conversion factor between weight and mass, if that's helpful. I like to bring up the rhyme that I made up. To convert from mass to weight, just multiply by 9.8. 1. I know. I used to only use 9.8, so there it is. So 9.81 is your answer. So to convert from mass to weight, just multiply by 9.81. And yes, I will say that to you many times, so hopefully that helps for you. If you have any questions, please let me know. Thanks.